Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all to the class of real analysis. In today's lecture, we are going to discuss very important topic, that is the monotonic sequence, and later we will discuss monotone convergence theorem. This is chapter number 10 of chapter number 3, numerical sequences and series, from the book of Principles of Mathematical Analysis by Walter Rudin. Firstly, we will discuss how can we define monotonic sequence. A sequence Sn of real numbers is said to be monotonically increasing if Sn is less than or equal to Sn plus 1. That is, S1 is less than or equal to S2, S2 is less than or equal to S3, S3 is less than or equal to S4, and continuing this process. In other words, you can say every next term is larger equal than the previous term. Then the sequence is called monotonically increasing sequence. On the other hand, a sequence is called monotonically decreasing if we reverse this sign, that is Sn is bigger than equal Sn plus 1. That is, every previous term S1 is greater than or equal to S2, S2 is greater than or equal to S3, and continuing this process. This shows that every previous term is greater than or equal to the every next term. There are some examples related to monotonically increasing and decreasing sequence. This is the first example of monotonically increasing. You can say every next term is either greater than or equal to the previous term. The first term is 1, the second term is 2, third term is also 2. So second term is greater than the first term, but second and third terms are equal. So this complete the inequality sign less than or equal. Similarly, the fourth term is bigger than the third term, fifth term is bigger than the fourth term, and fifth and sixth term are equal. So either the terms are greater or are equal than the previous terms. So that's why this sequence is a monotonically increasing. While this sequence 5, 4, 4, 3, 2, 2, 1 up to so on, this is a monotonically decreasing sequence. Every next term is either less than or equal to the previous term. In the third, I have written the formula. This is the example of monotonically increasing in general form. This is the nth term or the last term of the sequence, or a general term you can say. This is monotonically increasing sequence because when you put n is equal to 1, this gives first term 1 square, that is 1. When you put n is equal to 2, this gives second term, that is 4. When you put n is equal to 3, this gives 9. When you put n is equal to 4, this gives 16, and up to so on. So you can see here every next term is bigger than the previous. So this sequence is a monotonically increasing. Similarly, the sequence Sn is equal to 1 over n. This is a monotonically decreasing sequence. The fifth one is an important sequence. I have formed this sequence as for every even term sequence, even term or odd term given by the same formula, that is 1 over n. So if you put n is equal to 1, from here this becomes 2 into 1 minus 1, that is equal to b1. So this gives the first term, and formula you can use 1 over 1, which is equal to 1. So the first term is 1. When you put n is equal to 1 here, this gives 2 into 1, that is b2. This represents the second term, and which is equal to, by putting n is equal to 1 here, again this is 1 over 1. So this sequence I have formed in such a way that every term at a even position or odd position is are same, and it is given by the formula 1 over n. So this is a sequence which is a non-increasing sequence. You can see every next term is either less than or equal to the previous term. Here you may find some uh, terminologies in other textbook. I have written in many textbook the term non-decreasing and non-increasing are used for monotonically increasing and monotonically decreasing sequence respectively. Uh, Although Walter Rudin did not use this terminology, he just used monotonically increasing and monotonically decreasing sequence. But in many textbooks, you may find the non-decreasing sequence is actually monotonically decreasing, and the non-increasing sequence is represented by monotonically increasing sequence. Further, also in some textbook, you may find the terms strictly increasing and strictly decreasing sequence that can be defined as a sequence Sn is called strictly increasing if every next term is strictly greater than the previous term. Here you can notice that I have not written here equal sign. This is just greater than sign. Uh, on the other hand, if every next term is less than the previous term for every positive integer, then the sequence is called strictly decreasing. For example, the sequence Sn is equal to n. This is simply given by the integers. If you put n is equal to 1, this gives 1. For n is equal to 2, this gives 2. For n is equal to 3, this is 3, up to so on. You can notice that every next term is strictly increasing the previous term. So this is the strictly increasing sequence. Similarly, Sn is equal to n square, Sn is equal to n over 1 plus n are the strictly increasing sequences. Whereas the sequences Sn is equal to 1 over n, 1 over n square, n plus 1 over n, these are the strictly decreasing sequences. So it completes the basic concept of monotonically increasing and decreasing sequence, and I hope now you have a clear understanding about this topic. Now I am going to discuss a very important theorem. This is called Monotone Convergence Theorem, and this is very important related to your final exam. Uh, this is Theorem 3.14 in your textbook. This theorem says, suppose Sn is a monotonic sequence. This is given information. This is given. Your sequence is monotonic. Monotonic means it is either a monotonically increasing or monotonically decreasing. Then we have to show Sn converges if and only if and only if it is bounded. So this theorem has the two parts. When it is convergent, then you have to prove this is bounded, and when it is bounded, then you have to prove this is convergent. While the monotonicity condition will be used in both cases. Suppose the monotonic sequence Sn is convergent, then its boundedness can be followed from theorem 3.2c. I have already proved this theorem 3.2c, which is whose link is given in the description box. From this playlist, you can find this lecture that involves theorem 3.2c. In this lecture, I have shown that every convergent sequence is bounded sequence. So this complete the first part of this theorem. That is, if your sequence is convergent, then it is automatically bounded for any metric spaces. So you can watch this video in which I have proved theorem 3.2c. Next we move to its converse part. Conversely, suppose that your sequence Sn is monotonic and it is bounded. Now I will show this is a convergent sequence. Since suppose that the sequence is a monotonically increasing, because monotonic mean it is either in the category of increasing or and decreasing. So I will take here the case monotonically increasing, that is Sn is less than or equal to Sn plus 1 for every positive integer. The proof is analogous on other case. Analogous mean you can prove this for other case, that is the monotonically decreasing, with the same steps that I will share here. Okay. I have written since the sequence is bounded above. How this is bounded above? Because we have supposed your sequence is bounded. When you say a sequence is bounded, then by the definition of bounded, it is bounded above as well as bounded below. I mean to say a sequence which is bounded, it completes both of the property bounded above and bounded below. And further, you can notice that here every next term is bigger than the previous term. So if S1 is the first term, then it is automatically less than or equal to S2, S2 will be less than or equal to S3, and continuing this process, we can reach at the point this is less than or equal to Sn. It means you can say S1 is always less than or equal to Sn for all n. So this shows that a monotonically increasing is always bounded by this term, and this shows this is a bounded above. So if it is a bounded above, then the property of R, that is as R is a complete, so supremum property, there exists an upper bound of this sequence Sn. So let the supremum of this set Sn is given by the number S. This is the least upper bound property, which says that uh, if any subset A of real number R which is bounded above, has an upper bound in R. This is the this is due to the completeness property of R. This is called the least upper bound property of R. So as sequence Sn is bounded above, so the set given by the term of the sequence, that is S1, S2 up to so on, this is subset of R. R is complete. This set is a bounded above. So least upper bound property says this set must have a least upper bound. Say the least upper bound is S. What will we have to prove? We have to show the sequence is convergent. So we will prove that this sequence is convergent and convergent to this least upper bound. So this is our target to show. Now to show Sn is convergent to this least upper bound, let epsilon is a given positive real number. Since S is the supremum of this sequence Sn, this set Sn, S is the supremum of this number. Now I want to ask, if S is the supremum, epsilon is a positive real number, then is it possible that S minus epsilon is greater than S? This is not possible, because when you will subtract any positive real number from this real number, then automatically S minus epsilon will be less than epsilon. So S minus epsilon cannot be an upper bound of the sequence because it will always less than this real number S for a given positive real number epsilon. How much epsilon you take small, this number S minus epsilon will always less than S. It means when your S minus epsilon is less than epsilon, it means between these two real numbers, S minus epsilon and S, it must be that there exists at least one term of the sequence Sn lies here, because S is an upper bound. When you subtract epsilon, it gives another real number S minus epsilon which is smaller than this number S. So it must be that there must exist at least one term of this sequence Sn between these two numbers. Say this term is Sn, like you can say this is the 1000th term of the sequence, this is the billionth term of the sequence that lies in this interval. So I say there exists a term number n for which this term exists Sn. Hence there exists some positive integer n, that is the term number, such that this term Sn lies between these two numbers. So from this inequality, we have Sn is bigger than S minus epsilon. Say this is inequality number 1. Further, since Sn, this sequence is increasing sequence, by definition of increasing sequence, for every n which is greater than or equal to this capital N, Sn will be greater than or equal to Sn. This is the definition of increasing sequence, which says at every at a large suffix, the answer of your term will be larger. I mean to say, if you take n is equal to 1, this is n1, and if you take n10, this is the 10th term of the sequence. As 1 is less than 10, so, and if our sequence is increasing, then it says your first term, answer of your first term S1 will be less than answer of your 10th term. And in case it is monotonically increasing, it could be equal. So when for every n greater than or equal to this positive integer n, your Sn will be greater than or equal to Sn due to the monotonicity of increasing sequence. Now combine this, say this is 1, 2. Now combining 1 and 2, Sn is bigger than or equal to S capital N, and S capital N is greater than S minus epsilon. So this can be written as S minus epsilon less than S capital N and S less than or equal to Sn. Now, further, as S is an upper bound of our set Sn, as S is upper bound of this sequence, this set, so by definition of upper bound, every term of this set will be less than this number. You know, upper bound is a real number which is bigger than or equal to every term, every element of that set. So that's why if S is an upper bound, then S will be greater than or equal to every number of this set Sn. So this becomes S minus epsilon less than Sn and Sn less than S. How? Here I have omit this number Sn. So I left with Sn, S minus epsilon and Sn, and further Sn is less than or equal to S. For every positive real number epsilon, it is clear that when you add epsilon with S, then S will always less than S plus epsilon. So by combining these two inequalities, we have S minus epsilon less than Sn, Sn is less than S plus epsilon. From these two inequality, I have omitted this number S. By subtracting epsilon from each part, this gives s less than s less than by subtracting s from each part, sorry, this gives minus epsilon. This is s minus s. This is less than plus epsilon. And by using the definition of absolute, which says if x absolute is less than some positive real number a, then minus a less than x less than plus a. So by using this inequality, we can write this. This gives s minus s absolute less than epsilon for every positive integer n which is greater than or equal to n. And what does this show? This shows our sequence Sn converges to S, which is the definition of convergent sequence that we have to show. Now, regarding this theorem, I have some important facts that you must note. If we omit the monotonicity condition, that is, if we ignore the condition of increasing or decreasing, then the bounded sequence need not be convergent. And sometime in your exam, it can be asked that the converse of the theorem is not true. So, in case when you omit the condition of monotonicity, then bounded sequence need not be convergent. For example, consider the sequence Sn given by minus 1 whole power n. This sequence is bounded because it's lies between minus 1 and plus 1. For example, when you find its first term, this is equal to s1 is equal to minus 1 whole power 1, which is equal to minus 1. When you put n is equal to 2, this gives s2 is equal to minus 1 whole square. This is equal to plus 1. So all of these terms are either minus 1 and plus 1. So it oscillates between minus 1 and plus 1 for every positive integer n. So its values lies between minus 1 and plus 1. But it is not convergent because it oscillates between minus 1 and plus 1 and hence does not approach a unique real number. That's why this is not a convergent sequence, because all of its terms are either minus 1 and plus 1. So its answer is minus 1 plus 1. So this shows that the sequence was bounded, but it is not convergent. It is bounded above by 1 and bounded below by minus 1. So it completes our today lecture, and I hope this lecture was very helpful for you. And if you find this video helpful, please like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.